Lesson 27, calculating speed. We'll be able to calculate the speed of an object. Now, this is our second lesson in motion. So before we get too deep, let's go back. So motion's our new topic. And we're going to spend some time today talking about what motion means. And then also we're going to be talking about how we can calculate speed. What we did last lesson is actually unit conversion. And this was a bit of a short lesson at the end of the day. And it was after a test, so I wasn't too annoyed if you guys missed out on some of the content. But the idea of conversion units is we're going to have to be able to convert units in this topic. Sometimes I'm going to give you guys, this car moves at 60 kilometers per hour. What is that in meters per second? And you guys are going to have to know how to convert kilometers to meters and how to convert hours into seconds. Otherwise, you won't be able to do this. So in order to do that, I taught you guys, we went back over this, which you guys probably learned in maybe year 7, but how do you go from all of these directions? We said from kilometers to meters, we're going to times by 1,000, times 100, times 10, divide by 10, divide by 100, divide by 1,000. And then what we did was we talked about what these units here mean, what the units kilogram, kiloliter. These should be lowercase case, by the way, just so that you can make fun of me later on, because it should be kilogram. Kilogram. I think the G is capital. I think they're lowercase. Maybe I'm wrong. I think I might be wrong, but we'll figure that out. I guess it's not really too important. Kilo means 1,000. That's why you might say, oh, this house is 320K. It means 320,000. And milli means times 10 to the power of 0 is a thousandth. It's a very small amount in comparison. Then we talked about time, which we looked at hours, minutes, and seconds. And we did, well, that's going to be times 60, and these are all again times 60s. It's a bit different when we're comparing hours to days, but yeah. And then we looked at these non-base ones. Today we're going to talk about the non-base 10, so like inches and feet. So 1 inch converts to centimeters, and there's 2.5. You won't need to know that necessarily for this topic, but maybe one day you might be looking at a tape measure or your ruler and being like, what are these inches? What does that mean? Well, now you know how to convert them easily. Now, let's talk about speed. Now, before we can talk about speed and how we calculate speed, we're going to take a step back. We're going to take a few steps back to talk about the very first thing that we deal with motion, which is, what is motion? Motion is about movement. That's the main thing. When we talk about motion, movement, there are so many different types of motion. There's spinning motion, there's falling motion, there is pushing motion, pulling motion. You know, there's motion of one thing and there's motion of lots of things. And we're going to be dealing with how to deal with motion of all these different types. We're going to describe how we measure motion differently. And we're also going to discuss what causes different motion. But before we can talk about motion, we're going to talk about our basic friend here, which is distance. Distance is where I would like to start, because distance is something that we've all used before. I'd like you to just quickly jot this down, and then I want you guys to write down in your books, in your own, some units that you could use to measure distance. It can be any of the units that we know that we can measure distance. So I assume you guys are starting to write this down. If not, hopefully you are in a second. So our first distance is our first means of measuring motion. Now motion is more of
Do we have to write this down?
Yes, there's a pencil. Now remember that motion is more of a thing that happens over time. But I guess the idea is we need to have an understanding of what distance is, because if I'm talking about, oh, this car moved 2 meters in 10 seconds, you guys need to understand what meters mean. And this is why we started off with just a general idea of measurement. Distance tells us how far an object has traveled. Okay. Now it uses units that you guys might be familiar. Can someone call out a unit of distance for me?
Meters? Question mark.
Meters, perfect.
Yeah.
Can anyone give me another one?
Kilometers.
Kilometers. You could have centimeters. These are all great units of, you could have other ones. You could have feet, you could have inches, you could have parsecs, you could have clicks, you know, you could have stad or stadiums, whatever you want. These are all different units of measurement. Okay, I'm gonna give you guys one more second to copy this down before I change the slide.
Yes.
All right, so let's move on to the next idea. By the way, I've been experimenting with these slides to try to make them look a bit more artsy. I hope you guys like them because but yeah, I think this looks kind of cool.
It's crazy.
Can you guys actually still read it even though I've got this box up here and stuff like that? Because I was worried that you guys wouldn't be able to read it.
Yeah, we can read it. Beautiful.
Thanks, Brendan. So there is a bit of an issue with distance, okay? And you guys might not think that it's a bit of an issue, but there is a bit of an issue with distance. And I'm going to tell you what that issue is and how we can get around this problem. Let's just say a man runs for 5 kilometers. How far away from home is he? Well, a lot of you guys are probably thinking to yourself, that's an easy question, Mr. Greer. If a man is at home and he runs 5 kilometers, do you know how far away he is from home? He's 5 kilometers away from home. Done. Easy. Solve, like quick maths. I solved all of this. I solved all of motion. I'm finished. And I'll be like, yep, you know what? You're right. But I want to present to you guys an alternative. What about this guy? He does this. So he runs 2.5 kilometers away from home and then 2.5 kilometers back. Can you tell me, this guy in the green, how far is he, how long is he run for? Like what distance did he travel?
2.5, and then he just walked up and then came back.
So then how far is that in total? How far has he run in total?
5 kilometers.
So this person in green has also run 5 kilometers, yeah? But now his distance, how far away from home is he? He is 0 meters from home because he is at his home. And you might be like, okay, that doesn't make it as simple, right? Just because you know this person's run 5 kilometers doesn't mean you know where they are. What if I had this person, let's do a new one in blue. This one in blue, let's make it really, let's say that this one in blue, he runs 4 kilometers this way, and then he runs 1 kilometer this way. He's still run 5 kilometers, but his distance home is actually not 5 as either. His distance home is this distance here, which happens to be 4.12 kilometers. So he is also, this person in blue is also not 5 kilometers away from the house. We could take another person. Let's take this person in purple. This person in purple runs 4 kilometers, runs 4 kilometers this way, and then runs back 1 kilometer. So then when they finish, they are actually 3 kilometers away from the house. So we have this problem here. We know that even though this man runs for 5 kilometers, how far away from the home? We don't know that answer. They are somewhere between 0 kilometers away and 5 kilometers away. They can't get further than this. They can't get closer than that. We don't know how far away it is. So this is what we call a problem with distance. Just by saying this person traveled this distance doesn't mean you know how far away from home they are. They could have just run in a circle. You know, they could have just run in a circle and gone back home. And that circle just happens to be 5 kilometers. So we call this problem, we say the issue of distance is that it doesn't say how the object is moved. It just says how far it has. So what we do is we have 2 ways of dealing with this issue. The first is to talk about where that object is every second of its travel. That is an idea of speed, or like, and you're pretty much saying, oh, it's moving at 2.5 meters per second for the whole time. You know, then you know that where it's going to be. The second way to deal with that is to introduce a new term. Now, this new term, for a lot of you guys, is going to be pretty much, and a lot of you guys, if you want to replace this term with distance, that's fine, but it is still a new idea. That new term is called displacement. Okay, this is another thing I'd like you to copy down. Displacement is a measure of distance, but displacement must have a direction. So that's the first thing about displacement, is that displacement measures direction. So now we know, okay, how far away from home we've gone, because we can say, well, we've moved this far away and we've moved this distance. Displacement also only measures from the start to the finish. It doesn't care about what path you've taken to get there. It only measures the start to the finish. If you were, and we refer to displacement, I'll look at the picture first. This picture does a really good job of explaining how that works. What we've got here is we've got Edgar's Noodle Company. So what they do is that they make a bunch of noodles, and then, you know, they then put that into a box and they deliver that to a bunch of people. Okay, and this particular delivery driver goes down this road here, goes up to Jim's Bowling Alley, and obviously someone at Jim's Bowling Alley has ordered some noodles, goes through a vector square, travels another 1,600 meters, turns right at Scaler Street, and then drops another bowl of noodles off at Jade's Fashion. Now the question is this. Let's compare distance to displacement. The distance traveled is 2,800 plus 400 plus 1,600 plus 400. That's going to be 2,000. That's going to be 3,200. So the total distance traveled is 5,200, which is the same as here. Okay, but the displacement is not that. The displacement is measured from start to finish. I started the noodle company and I ended at this. That distance is 1,440 meters. That's my displacement. Luckily for you guys, I'm not going to get you guys to calculate these displacements. I'll usually give it to you. Saying that though, because I know there's a couple of probably nerds here, you guys can probably tell that if I drew this like this, hey, what do you know? It's a right angle triangle. I know this would be 800 meters, and I know this along the bottom would be 2,800 miles, whatever it is. I just want to show you guys that that's 1,200 here. If you square those two numbers and square root them, you could find out the longer side. I'm not going to get you guys to do that because, yeah, sure, I know that you guys all know your Pythagoras from last year, but this is supposed to be a science topic. We're not going to go too deep into the maths. But I can't just write 1,440 meters. I've got to also write the direction. The direction in this case is northeast. So let's just write northeast in here. And that's what the difference between a displacement and a distance. They can be the same thing. You can run 5 kilometers north and have a displacement 5 kilometers north, but they can also be different because you're only measuring from start to finish, and it must have a direction. Because it has to have a direction, displacement has a special name. We refer to it as a vector because it has a direction. And because distance doesn't have a direction, it's known as a scalar. Scalars have no direction. Now, this is going to be important later on because later on what we're going to do is I'm going to say to you guys, okay, well, so I almost think we're going to talk about speed in this way. I like to sometimes think about displacement as like an upgrade. It's like an upgrade to distance. You know, it's a level up. You've got like distance, which is like the boring base tier level. It's like, oh, great. Well, I know that I've traveled 5 kilometers. Great. Displacement's the next level up. It's like, oh, not only do you know how far you've traveled, you know which way you've traveled. And also it's better because it doesn't deal with all these ugly turns and corners. It only deals with straight from A to B. How far did you go? This can be really good if you're just trying to figure out, well, what's the fastest route? If you're trying to find out what the fastest route from this noodle company to the fashion store, right? You've got this distance here. You've got this displacement here. You want to find out what is the shortest time to take to cover that displacement, rather than knowing, well, what's the shortest distance or what's the, that's just another way to think about it. Are there any questions about displacement or things that people don't understand?
No.
All right, thanks, Alethea. Now we'll keep going then. Displacement. Remember, it's just an upgrade on distance. It just means it's just how far you've gone, but also which way have you gone. So now we're talking about speed. I'd like you to copy this down.
Damn. I kind of.
Oh, sir.
Oh,
Upgrade.
shit. Hectic, right?
All right, bye.
Go.
Guys.
Okay.
I wasn't going to point this out, but I
like that.
I actually spent some time stuffing around with this. Grab a look at this.
That looks slick. I like your pen.
So that's the same pencil, but I've like applied like a filter to it. And I was like, yeah, people will get that. And I was like,
okay.
Slick as.
Okay, this man.
Okay, I see
I
you,
know what it
sir.
is. I see.
I kind of wanted to do this with a couple of the slides and stuff, but like I guess because the idea is like it's just we're just talking about speed. Like we could probably do slides like this. Like I kind of should have done more of this with probably genetics, but I didn't want to like get too intense. Okay, so what can I tell you about speed? Speed says how much an object's distance has changed over time. It's speed. When you break speed down, it's distance over time taken. Distance traveled over time taken. If you are walking and it takes you, like, if you're walking and it takes you 10, you go 10 kilometers in 1 hour, that means you're traveling at 10 kilometers per hour. That's just another way of writing it down. Now, instead of writing distance traveled over time taken, we sometimes shorten it down into this formula here. V, which is going to be speed, is equal to distance divided by time. Now, you might ask, why have we chosen V instead of S? There's a reason for that. We're going to cover that in a little bit later on. At the moment, I'm just happy if you guys can accept that it's, if you guys can just accept that it's V because it's just V. The units there are many, many units of speed, just like there are many, many units of distance. But the common ones that we're going to be using is meters per second, kilometers per hour, and centimeters per minute. Now, and we're also going to have to deal with how to convert one thing to another thing. So that's something else that we're going to have to work on. Let's talk briefly about what these mean. Now, if you think about them, meters per second actually means a distance traveled meters in an amount of time, seconds. So it's just a way of saying meters per second, just a way of saying distance meters per time seconds. Now you can mix and match these. You can have kilometers per second if you've got something that's moving like super fast. Like we're talking kilometers per second. We're talking about something like a subatomic particle fast or something. You got something like, instead you could have something really, really slow, like something like meters per hour. So that might be like, I don't know, that could be the speed of a snail or a tortoise or something. They only go 1 meter every hour or something. I will point out one last thing. Sometimes people in books and sometimes in tests are lazy. Because you've got seconds on the bottom here, you could think about that as being seconds risen to the power of -1. This is from your index laws. When you write something to the power of -1, it puts it on the bottom of the equation. This is just another way of writing meters per second. Just so you know, it's the same thing. It's just being written a little bit differently. Have I got any questions on speed calculations yet?
No.
All right, good, because we're about to start doing some actual calculations now on speed. So let's jump in and try some actual calculations. So we're going to do 3 in total. These are all pretty simple things, but we're just going to get the basics done so that we can figure it out. Let's do this one on the left first. I'd like you to copy it down. You don't have to, if you want to just copy down the working out, that's okay, but I'd like you to get this written down. I might give you guys a second to do that too. The average speed of an airplane that travels from Perth to Melbourne, a distance of 2,730 kilometers by air, in 3 hours is.
Wait, where's Perth?
Perth's on the other side of Australia.
Oh, like South Australia?
West Australia.
Oh shit, okay.
The capital of Western Australia.
Ah, lol. Okay.
Okay. So let's work out how you would solve a question like this if you were given it. Well, you would write down V equals D divided by T. Distance to your speed is your distance traveled divided by the time. The distance traveled in this case is 2,730 kilometers. 2730 kilometers. And it does that in 3 hours, divided by 3 hours.
Don't you have to convert it to like minutes? I mean,
No. So I'll show you what happens, right? Because we are not converting the units, we've got kilometers and hours. Our final answer will be in kilometers per hour. Okay? Because we're using those units. Now, if we were using meters and seconds, then our final answer would be in meters and seconds. You're actually, Brendan, you're actually quite on the ball, because that's going to be the next thing on the next slide I'm going to talk about. So you're actually a little bit ahead. So yeah, that's all right. But if I put this in my calculator, 2730.
it's 910.
910.
Yeah.
Kilometers per hour. Beautiful. And that's it. That's the speed that they're traveling. It's 910 kilometers per hour. By the way, though, well, actually, I'm going to talk about this in another lesson, but I will point this out now. Notice that this says the average speed. That means that on average, it's going 910. There may be some times where it's going faster than that. There may be some times when it's going slower than that, but on average, it's 910. Let's go have a look at something that's a little bit slower. The average speed of a snail, it takes 10 minutes to cross 90 centimeters of concrete. Paving stone in a straight line. So it's going in a straight line. So we're just going to calculate this. Velocity equals distance divided by time. We want to know the speed. The distance traveled. Yeah, it's going to be pretty easy. It's going to be 90 centimeters in 10 minutes. It's going to be 9 centimeters per minute. Now, making sure that we've got our units down as well, because we want to make sure that we know how quickly that thing is moving, but also what its units are. Because if we've thought about this, right, if you had something going at 9 meters per second, it's going to be moving a lot faster than a snail moving at 9 centimeters per minute. So knowing what these units are pretty important. Speaking of units, let's grab a look at why units are important. So a car travels 60 kilometers in 1 hour. How fast is that car moving in meters per second? So let me show you guys a couple of bits and pieces about how you could do this or different ways you can solve this problem. So the speed, which is distance over time, which is 60 kilometers in 1 hour, that's going to be 60 kilometers per hour. That's fine, but that doesn't help us solve our problem. That doesn't help us calculate meters per second. So the best way is to take your distance. Take your distance, which is 60 kilometers, and convert that to 60,000 meters. Okay, and your time, which was 1 hour, becomes 3,600 seconds.
Wait, what?
I got that by taking 1 hour, multiplying it by
I'm so confused.
1 hour,
Oh.
multiplied by 60 is 60 minutes.
But can
Times
you
by 60 again is 3,600 seconds. Now, because I've done this so many times, I know that off the top of my head. Do I expect you guys to know that off the top of your head? No. I actually expect you guys to be able to be doing this. And of course, if you had like 1.5 hours, then you would multiply it by 60 and then 60 again. It just so happens that I know that if you want to go from hours to seconds, you multiply by 3,600. But, you know, doesn't matter. So now let's do this equation again. V equals d over t. The speed is going to be, this time the distance traveled is 60,000 meters over 3,600 seconds is going to be 60,000 divided by 3,600 seconds, 16.66, we'll go with 16.67 meters per second. You can convert and you can compare these two things together. Now, yeah, so you're not going as many meters per second as you are going kilometers per hour. But you think about it, you're going 16 meters. That's pretty far in 1 second. So, like, and you think about 1 second is 1, 2, 3. They're going 16 meters, like 17 meters. Every one of those counts. So that's a pretty fast-moving car. And
wait, do we have to write V equals D divided by T all the time?
You should, yeah, because then it shows me that you understand what you're doing. You understand the steps needed.
All right, cool.
Now, I do want to show you one extra little thing here. All right? The extra little thing is that all we pretty much did, this is more of an advanced technique. You don't have to use this advanced technique if you don't want to. To go from kilometers per hour to meters per second, what we did was we multiplied the top by 1,000, because kilometers, that would turn into meters. We multiplied the bottom by 3,600, which means essentially we multiplied by so essentially what we did was we took kilometers per hour and we multiplied by 1 on 3.6. Or you could say we divided by 3.6. So there's a rule, and I don't like this rule. You might be like, why are you teaching us a rule that you don't like? Because I know some of you guys are, love formulas. But I hate this formula because I always forget it. I would much rather do this. Yes, it takes more time, but I know what I'm doing. But if you want to, you can use this. Kilometers per hour. If you take that and you divide it by 3.6, you'll get meters per second. If you take meters per second and you multiply it by 3.6, that'll take you to kilometers per hour. So if you had, like, let's do an example down the bottom, 100 kilometers per hour. If I divide this by 3.6, then that's going to equal 27.8 meters per second. That's a way that I can quickly and easily transfer from one thing to another. I don't like this method, but you guys might, find it useful. You might want to write it down, use it on use it in tests. But yeah, I would prefer instead just to convert 100 kilometers to 10,000 meters and 1 hour to 3,600 seconds. Bang, bang, we're done. We got 27.8 meters per second. But it's up to you. I just wanted to show you that in case you cared about it. Now, the next thing is changing the formula. Okay, the car is traveling, and this is how are we going for time? Oh, we've got some time. We should be able to get through this whole lesson. I'm actually pretty happy with that. A car is traveling at 100 kilometers an hour down the freeway to get to Geelong. So here's Braybrook. Here's Geelong, and it says here Geelong is 67 kilometers away. how long will it take to arrive? Okay, we're traveling at 100 kilometers per hour. So this time we've got a bit of a different question. We write down V equals D over T. This time we don't actually want to calculate, V. We want to calculate T. We want to work out how long it takes. Now to work out T, we're going to have to manipulate this equation. Or
Is it like when you flip it?
yeah, we could flip it. We've got a couple of choices if we want to flip it or if we want to move it. I'm going to do it in 2 steps, but you guys might want to do it in 1, but I'm just going to do it in 2 steps just so we're familiar with it. What I'm going to do those 2 steps is I'm going to multiply both sides by T.
Oh, scary.
Which is going to cancel that down here. That's going to give me VT equals D. Now this formula is really good. If it said we were traveling at 60 kilometers an hour for, 3 hours, that'd be a great formula for doing that. But I don't want to know that. I want to know time. So now I'm going to divide both sides by V, which gives me T equals D divided by V. Brendan, if you were more of a fan of the old flip method, yeah, sure, you could do that. That would look like this. If you're interested, V equals D over T. If I flip these upside down, what that will give me is 1 on V equals T on V. T on D. And then if I multiply both sides by D, that's going to give me D on V equals T. Same formula, but it's using the flip method instead. Up to you though.
Oh.
You could even do the cross multiply method and you'll still get to this answer at the end. So now that we've got that, let's use this. T equals D divided by V. We're traveling 67 kilometers. We're going at 100 kilometers every hour. Therefore, we can figure out it should take us 67 divided by 100 is 0.67 hours. Or multiplying that number by 60 tells you it's about 40 minutes. But that's a way how we can flip the equation around to deal with it. If you wanted to find distance, you could use that formula. So you need to get a little bit familiar, and this is going to require a little bit of math skills, is being able to flip around an equation. We're going to add more equations to these as we go, but at the moment we're just dealing with just this equation. So I would love you to get comfortable. Quick question though, to anyone else. It says here on this graph that that's actually not the answer. It says here it's actually 54 minutes. Can someone tell me why? It's just the basic answer. Why is it not 40 minutes? Why?
Don't trust Google Maps. Google Maps is a scam.
Oh, you reckon it's a problem with Google Maps?
Yeah, just don't trust Google.
I believe there are external factors like traffic.
Yeah,
there are external factors like traffic. Is there any other thing here that might affect how long it takes you to get?
Traffic is spelled with 2 F's though. My bad.
Is there any other factors?
So wouldn't it be the curves on the road?
Yeah. Oh, the lights.
Oh,
facts.
I just think about how fast the car's traveling.
What do you mean by that?
Like you could be in a Lamborghini, you'll get there in like 30 minutes, or you could be in a Toyota and you'll be there like in an hour.
Yeah,
so like,
but I have said that you're traveling at 100 kilometers an hour.
Yeah, but like it's not always 100. Like, come on, like who maintains a consistent 100?
That's what I was looking for, Brendan. You nailed it. It's not always 100. Like, if you're driving through Braybrook, you're not going to be going down the streets unless you're crazy at 100 kilometers an hour, because there's going to be stoplights and stop signs. Maybe you can drive down 100 kilometers an hour for most of it on the freeway, but in Geelong there are some streets there that you've got to slow down for. But yeah, traffic and curbs in the road, these are also really great ideas, guys. This is a simple little question here, and I know that students get these types of questions wrong. It's just being able to think outside the box. Yeah, sure. I really want you guys to be able to do these calculations. But if you can't also say, well, does that calculation make sense? Then we're in trouble. And I think, yeah, but you can sort of see 40 minutes to 54 minutes is actually not too different. If we were talking about 40 minutes to like 10 hours, then I'd be like, ooh, maybe we made a mistake in our calculation. But we know that we probably haven't, because we can maybe account for some of the speed loss because of these other factors. Let's now look at the last topic, which we've got about 10 minutes to do, about 15 minutes actually to do. Yeah, okay. So the last topic is velocity. Now, velocity is, again, velocity is like an upgraded version of speed, okay? Now, it is, again, very similar to how displacement is an upgraded version of distance, except velocity is instead of being distance over time, is displacement over time. Now, that's important, okay? So let's just say, and I'm going to talk about the comparing displacement and time in a second. Velocity is a vector quantity, which means that it has a direction, which is what I just saw. Whereas speed is a scalar quantity. It has no direction. And now you can see why we use the symbol V. We use the symbol V because V stands for velocity. Sure, we can still use V to mean for speed as well, but velocity is V. And you guys probably have seen velocity, maybe velocity points. Maybe you may have seen for like air travel, you may have seen velocity in other places. Terminal velocity, how quickly something falls. But velocity is essentially how quickly something speeds. It's pretty much just speed. Velocity is just speed. The only difference is that we're saying, well, what direction are we going? I'm going to give you guys a second longer to copy this down before I change to our very last slide today, which I'm actually really impressed with how much we've gotten through. I really kind of wish I made this bold here, because it's a new idea too.
Wait, do we have to write that down?
Yep.
Oh.
That's why I'm leaving it up for so long.
Oh, I didn't see that. I was watching something. Damn.
I'll leave it up for a bit longer, Brendan, but I'm not going to leave it up for too long. Yeah.
Yeah, just give me a minute.
We've only got a minute. We all good? Is anyone confused by anything so far? We seem to be making sense of this.
Yeah, I'm getting like
Yeah.
the gist of it.
Yeah.
I mean, I only remember earlier because like last year we learned about it.
Oh, did you learn about it last year?
Yeah, I'm pretty sure because I remember learning this. It was either last year, but I remember learning it.
Okay. Did you do STEM, or did you do was it just in science class?
See, I can't remember that. I think it was either.
Right.
Yeah, I'm pretty sure it was just in science. I don't know. I can't remember.
STEM was trash.
Because like I don't think I taught this in science last year, but
No, because I remember learning about it. I'm pretty sure we learned about it.
Yeah, I remember learning it a little.
Yeah.
Equals D.
Well, again, you're supposed to we're supposed to teach it in year 10. So I'm actually surprised that you guys actually have heard of this before. And that's why I was surprised so many of you guys did well, because I know that I didn't teach it to my year 9 students. We just didn't get a chance to do it. So it's a bit interesting, but that's all right. I'm glad. It means that this is not as difficult for you guys. Ultimately, ultimately, if you understand this equation from today, then that's the main part, really. That's the main important part anyway. I'm going to jump ahead to the next slide now, just because I want to quickly do this, because I've got like 5-10 minutes left before the bell 10:36 goes. So let's just do this last little bit here. So we're going to compare velocity with speed. And this is the very last slide, and this is the last idea here. So let's talk about this. A man is racing his daughter across a park. This is a park, by the way. He runs around the edge while she races across the middle. It takes them both 100 seconds to meet up. So the little daughter is going, we'll draw her here. She's going across the path. Whereas the man, the father, he's going around the edges of the path. Now, let's compare some factors, okay? Oh, I didn't actually get you guys to write this down. You don't have to write this down, I guess, if you don't want to, because there's a lot of information here. But if you do, it could be useful for you later on. So I'm just going to leave that option up to you. Okay.
Wait, isn't the girl gonna win?
Well, no, I've said it takes them both 100 seconds. So they meet up together. I've just said it, they meet up at but if they're going at 100, we're going to explore what happens. We're not going to say they're running at the same speed. If they were running at the same speed, the daughter would win, yes. So in this case, the distance that they both travel, the daughter travels 28, the daughter travels 28 meters.
Questions 1, 3, 5, 8.
Whereas the father, he's traveling 40 meters, okay?
Oh.
Because he has to travel 20 meters plus 20 meters, okay? Now their displacement, if they start here and they end here, the displacement of the daughter is 28 meters, because that's how far it is from start to end. The displacement of the father is 28 meters. I'm going to give you guys a second for that to sink in. The displacement is the same for both of them because, and technically we should say something like northeast, because they're both traveling. In this case, they're both traveling 28. They're both from start to finish, they're traveling 28 meters. The only difference is, you might say, that the father's traveling that in a longer, it's taking a longer route. It's interesting here, the daughter, her distance and her displacement are the same, but the father, his distance and displacement are different because he could have taken a faster route if he went across. Now let's look at their speed. So the daughter's speed, she travels 28 meters in 100 seconds. That means she's traveling at 0.28 meters per second. The father travels 40 kilometers in 100 seconds. So that's going to be 0.4 meters per second. We were right. The father has to run faster to make sure that he gets to the corner at the same time. Hopefully that makes logical sense to you. It's like, oh, the father needs to because the father has to run a longer distance, he has to run faster. If the father ran the same distance, the same speed, then, you know, the daughter would get there and she'd have to wait for the father to get there. So they have to run at different speeds. What about their velocity? Well, velocity is their displacement over time. So the daughter's displacement, remember, velocity equals displacement over time.
Wait, how old is the daughter there?
Oh, it doesn't matter, but I've assumed that, like, that's what I said. Maybe it's like a little, like, 6-year-old daughter and the father's got long legs. So, like, it's sort of like, I'm like, okay, it could make sense that that's why I chose this scenario. It makes it the father can run faster than the daughter. Whereas if I had it the other way around, it might be like, no, that's not possible. So the displacement of the daughter is 28 meters and 100 seconds. So the displacement, the velocity is 0.28 meters per second. Oopsies. 0.28 meters per second northeast. And the father's velocity is his displacement, which was 28 meters in 100 seconds. So it's 0.28 meters per second northeast. They both have the same velocity, and that's the kicker here. They have the same velocity. His speed is faster, but if we're just looking at velocity, how long does it take to get from one point to another point? This velocity is the same. And velocity is displacement over time. This is how those two things are different. And I like this slide because it compares everything. We can see here that distance versus displacement are different, which means that velocity over speed is different. Ultimately, when we talk about velocity, we're talking about, well, how far did they travel? Ultimately, the father traveled from here to here, and it took him 100 seconds. So it doesn't matter if he took this path, if he took this path, if he took some crazy path like this. Let's say that path is, I don't know, more like 50 meters. It doesn't matter as long as he did it in 100 seconds, then that would mean that he would have, his velocity would be the same. All right, ladies and gents, that's it. What I'd like you guys to do before Friday is, oh, okay, you know what? Let's do this.
That's a little too much work.
Let's do that. There we go. I'd like you to do questions 1 to 3 of 8.2 before Friday. And then on Friday, I'm gonna set the other section 5 to 8 to be done by next week. I'm gonna put that on the classroom as well, so you guys know what the homework is. And yeah, if you want to keep working, if you want to do 5 to 8 as well, because you want to make sure that you don't fall behind, then that's up to you. But that's going to be the homework.